Okay, in this example we're going to look at some basic properties of relations. And for our first example, we're going to use a really simple situation. We're going to have our first set of possible numbers be 1, 2, 3, and 4. Just to illustrate some of the properties of relations, and we're going to define our relation between A and itself. We're going to define a relation like this. So our relation is going to be a mapping between x and y for x is less than y. So our first step with all of these problems is going to be, okay, what are the pairings, if you like, in our relation set? So we can figure all these out reasonably easily in this example, and we can write them like this. So our first example is going between the x of 1 and the y of 1. So checking that out, we could say, okay, in our pair, if x is 1 and y is 1, does this relation hold true? Well, no, it doesn't, because 1 is not less than itself. If this was equal to, this would be true, but we know that this pair here is wrong. It shouldn't be part of our relation. Next example, 1, 2. Yes, this does hold true, because for x is 1, y is 2, x is less than y. So you can kind of see the pattern here. The next one, obviously, is going to be 1 and 3. The next one can be 1 and 4. You can see the pattern I'm going through here. The next one is going to be, continue down here, 2 and 3. One after this is going to be 2 and 4. And our final one is going to be 3 and 4. And that is, if I haven't made any mistakes, the complete set of the relations that we have. Now, that's the first step of our relation problem, but most of the relation kind of work you'll be asked to do is what are the properties of these relations. So typically you'll be asked to generate that and then answer some questions about it. And they'll usually be along these lines. They'll usually be, is this relation reflexive? Is this relation symmetric? Is this relation transitive? And is this relation anti-symmetric? And once you've figured out those four things, you can decide whether your relation is an equivalence relation or whether it's a partial order, and you can figure out a whole lot of things about it. But it can be a bit tricky to figure out and remember what these four are. So we'll just go through them quickly for this example. So the first one, reflexive, is actually pretty simple. It's essentially asking for all the members of the first one of these sets, so all the members of X, do you have that map to itself? So you can think of it in this example of saying, okay, for 1, for example, do we include in our relation the set, or the example 1 to 1, and 2 to 2, 3 to 3, and 4 to 4? And for this set, no, we don't, because x is less than y. If x was less than or equal to y, we would also have 1, 1, 2, 2, 3, 3, 4, 4 in this relation up here, and it would be reflexive. But in this case, nope, it's not reflexive because we don't actually have any examples where x is mapped to itself. Okay, so this is not a reflexive relation. What I'm doing here, by the way, is the standard way to react to relations is to try and look for all the examples where it is true. Actually, the best way to test for these four things here is just to look for a single counterexample, so a single example of where this is not true. So for our first one here, the fact that it doesn't include 1 to 1 means this is not a reflexive relation. Okay, and now next, so to test whether it's symmetric, symmetry testing, I write it like this. You're asking yourself, okay, for the mapping of x to some y, does our set also include the mapping in reverse? So y then mapped back to x. So, for example, for a set to be symmetric, in this particular example here, we'd go 1 to 2 and 2 to 1. Or 1 to 3 and 3 to 1. Or 1 to 4, 4 to 1. 2 to 4, 4 to 2. Now what we can see here is this is not a symmetric relation at all, because we've got 1 to 2 and we don't have the corresponding 2 back to 1. So that's the first counterexample we found, and because we found one counterexample, we know this relation is not symmetric. The next one we're going to do is transitive. So you can remember the transitive like this: for x mapped to y and y mapped to z, then the relation should also include r mapped to z. So this is saying if you have a number mapped to this and that number mapped to a third number, then the relation should also include the mapping between the first and the third number. So to give you an example, if we had, for example, 1 to 2, and then we have the mapping of 2 to 4, for a relation to be transitive, it must also include the mapping of 1 to 4, so the ends of those sets. And actually, if we look at this example, it's got that in it. We've got 1 to 2, we've got 2 to 4, and we also include 1 to 4. So this is actually a transitive relation. It is transitive. There are other options in here which don't hold to this, but we don't have any counter examples. Right? So that's why we think this is transitive, even though it's not clear. Like, so we have 2 to 3 and 3 to 4. We also have 2 to 4. So that is an example of a positive, so that holds true. But we don't have anything, say, going from 1 to 4 and 4 to 8, but not 1 to 8, which would be a counterexample. Now the final one is, I think, the trickiest. It depends on how you think about these things. Antisymmetric. So an antisymmetric relation, or a relation is antisymmetric if for all the mappings of r to y and y back to r, it also, or it states that x equals y. Now, a couple of points here. Antisymmetric does not mean not symmetric. They are two different things. So you can find some relations, although it's not that common, where it is both symmetric and antisymmetric at the same time. And I'll come back to that in a later example. In fact, if this was a less than or equal to relation, you would have one of those examples where it is both symmetric and antisymmetric. But in this particular case, again, we're looking for a counterexample. So here we're looking for a mapping from x to y and then from y back to x where x is not equal to y. So what we would be looking for to find a counterexample here? A counterexample would be having 1 to 2 and then 2 back to 1. Because therefore you've got a mapping like this, but 1 is not equal to 2. What you'll notice here is that we don't actually have any mappings that go backwards. So we don't have any 1 to 2, 2 to 1, 1 to 3, and then 3 to 1 because of the nature of this particular relation. So because we can't find any counterexamples, this is an antisymmetric relation. Even though we don't have any clear cases where x is equal to y, it is antisymmetric because we don't have any counterexamples. So we'll finish up this first example here, but I'll do some more complicated examples in the next couple of videos.